All right, welcome everybody to the chapter 24 and 25 review. So we're going to cover two chapters, and the two topics that we're going to go over this week are potential and capacitance. Those relate to chapters 24 and 25 respectively. And yeah, we're going to go ahead and just jump right into an overview of potential itself, and then we'll look at some problems, some applications. So I have mentioned this diagram and gone back to it a few times this semester. This sort of helps us relate our different topics together. So far in the semester, we've spent the last few weeks going over forces, the electrostatic force specifically, and fields, which in this case, the electric field. And we have equations for calculating each of these due to a point charge. The force equation is F equals KQQ over R squared. Of course, it is a vector, and there is some other more robust notation involved. So I'm just going to put this here. I don't even know that I've necessarily written out this definition, but the r hat there is just a unit vector that points radially. And that just tells us that the force is radial according to the charges involved. And this is what gives our force vector its vector definition. Now, the other vector that we've talked about is the electric field. And remember the electric field, the way we found it is we took our force divided by little q, the thing that's experiencing the force, and we get a definition here, kq over r squared, for the effect that the charge, big Q, has on the area around it. Even if there are no little q's present, we can say, yes, this big Q is producing some electrical effects in the space surrounding it, and we would know, should we put a charge in its vicinity, how it would interact with the field. And this one also has a little r hat, which I have, again, it's just there to say this is a vector, and this points radially. Okay, so this week what we're going to do is we're going to define two other terms. The first one is the potential energy, and this is going to come up in a few problems, but I'm just going to go ahead and put it here right now. And I'm going to start here because we did this in physics 1. We defined the potential energy when you have universal gravitation. You have a force, gmm over r squared, and the potential energy between any two masses is gmm over r. And the way you get it roughly is by doing the negative integral of the force with respect to the distance. And specifically, it is a path integral. And so it turns our force vector into a scalar. And in physics 2, we're going to have a similar one. I'm not going to go through the derivation, but there is a negative sign. There's some stuff with infinity involved. But what we need to know is just that our potential energy is K, big Q, little q, over, let me get that one more time, little q, over R. So again, this is a scalar. And just as in physics 1, for each pair of charges, Q and Q, you're going to have a potential energy between those charges. And if you want to find the potential energy of any configuration or charge arrangement, you just add up all of the potential energies due to each pair. Now, the last thing that we did not have a corollary for in physics 1, but which we will have in physics 2, is called just the potential. So this is going to give some people some trouble, and that's fine. You're not the first ones to have trouble keeping these terms straight. But the potential is different than the potential energy. Why do we reuse potential? Well, that's just, I guess, sort of the way that the cookie crumbles. We're going to have some other terms that are going to come from the potential. But for right now, what we just need to know is that this is called the potential. It's different than the potential energy. And that the way we get the potential is we can do one of two things. Either we could take our electric field and do the path integral, or we could take our potential and divide out the charge little q. So we're just sort of following the symmetry of this diagram, right? Up here, we divide out by little q to define our electric field. Here, we'll divide out by little q to define our potential. And if we do that, we're going to get that the potential is equal to k big Q over R. This potential is also a scalar, which is very nice because it means that we don't need to worry about the superposition principle that we had to do with the electric field last week and the week before. And so, that makes our life a little bit easier because we can just add our potentials together. The other reason why potential is going to be so important and why it is actually the concept that we carry forward with us into the next few weeks is because in physics 2, when we are constructing circuits and we are causing electricity to flow, what is actually flowing there is electrons, and electrons have a standardized charge of negative 1.6 times 10 to the negative 19th coulombs. And so by just describing the potential at different points, we can automatically infer what's going to happen with the electrons that are flowing through a circuit. So that's why potential is very handy. Now, I did mention that as we did a line integral over here, we could also do a line integral here to derive the potential from the field. And this is going to give us another equation that is very different. That is very important. So it's going to look different, but it's just the definition, that path integral. So here it is. It says that delta V is equal to the negative integral of E dotted with ds. So this is a path integral, which you may have seen before. If you haven't seen it, it's going to be okay. You're not going to have to actually do a path integral in this class. Typically, the way that you're going to do this is to just calculate a one-dimensional integral. So something like the x component of the electric field integrated with respect to x, or the y component integrated with respect to y, or so on. So I'm going to just write one of them down, but we'll typically just do, say, the integral of e sub x dx, or e sub y dy, or e sub z dz. But that's typically the way that we're going to use this equation. Okay. Now, what I do want to mention is that this delta v right here, which is the potential difference between two different points, is called just that thing I just said, the potential difference. And I want to take a second here to really emphasize that we now have three different things that you could be asked to calculate at any given time. We have the potential energy right here. We have the potential, which is just V, and then we also have the potential difference, which is delta V, the change in the potential. And it's actually a difference between the potentials at two different points. So step one is to make sure we keep those three different names separate and their respective definitions based on what the problem is asking us to calculate. And cool. So in light of that, I also want to mention that there's one other name that you will see for potential difference, and that name is that this is what is called the voltage. So I'm going to go ahead and write it down here. You'll also hear this called the voltage, and as promised, this is going to be the term or the concept that we carry forward with us into the next few weeks as we start to assemble circuits. So if you've ever interacted with circuits or electronics in any way, you've likely dealt with a voltage. You've certainly had something that you had to plug into a certain voltage, some electrical device that you needed to operate. You needed to plug it in to some voltage source rated at a certain voltage. But what the rating is actually there is a rating of a potential difference between the two terminals of your source. Okay, so first problem we're going to deal with is going to deal with potential difference, and we're going to use the equation that I have right here, and we're going to see how to put that into practice. So let's go ahead and take a look at the first problem. And this first problem, we actually have a graph, and hopefully we're sort of catching on here. Just as in physics 1, whenever you see a graph, you're typically thinking, okay, am I going to take a slope? Am I going to find an area? That would be a derivative or an integral respectively. Or am I going to do a, just read the points off the graph, which is a little bit easier even. And the graph is roughly shaped like this. And this is a graph for the electric field, the x component of the electric field versus the x coordinate. And in the problem, they're going to ask us about the potential difference. So as I mentioned, usually, we're thinking integral or derivative. And specifically, we've just defined that the potential difference is related to the integral of the electric field. And I gave you that secondary sort of definition. The way that we're typically going to use this equation is that the potential difference is equal to the negative integral of e sub x dx. Now, how do I find an integral from a graph? Well, that's going to be the corresponding area. And so our delta V is our V final minus V initial. And for this problem, we're going to relate that to the negative. We got to keep that negative sign, the opposite of the area under the curve. So the rules of calculus tell us that area below the x-axis is negative area and area above is positive area. Since we have a negative out in front, though, we're actually going to be adding voltage or potential difference when we're below the x-axis and subtracting it out when we are above the x-axis. So let's take a look at how to do this. In the first problem, and all these problems are going to give us an initial potential at the origin. Everyone's going to have a different one. My potential at the origin is 20 volts. So we'll call that my V initial, 20 volts. And yeah, the units, by the way, for potential are volts. It'll be the same for potential energy. The units for potential for potential and potential difference, the units are volts. For potential energy, your units are joules. Those carry over from physics 1. Okay, so first part is they ask us just to find the electric potential at x equals 2 meters. And x equals 2 meters happens to correspond to this point right here. So what is my potential at 2 meters? That would be some V final, where I'm going to plug in the V initial given right here. And then we'll set that equal to the negative of the area, where the area is just the area from the origin right here out to x equals 2. You just have to find the area of this little triangle in there and then solve for V final. In the second part, they ask us to find the greatest positive value of the electric potential in this whole run from beginning to end. Now, in order to find out what that value is, we need to figure out where it occurs first. So this is actually, at first, a bit of a conceptual problem. And this goes back to the idea here that the area below the curve is negative and above is positive. However, our potential varies with the opposite because we have the negative sign out in front. So what this means is if I have a negative area, if I'm below the x-axis, I'm actually gaining potential. My potential is increasing. So conceptually, that means that we're gaining potential down here in this little area, and then we're losing potential over here. Now, if I want to know where the potential is at a maximum, it would be when I've gained as much as I can, but I'm not losing any. In other words, right here, before we start to decrease the potential, that's going to be where our maximum potential occurs. All right. Now, in order to then calculate what that potential is, that will be a V final. We'll use the same V initial, and now our area on the right-hand side is going to be the area of this whole section that is below the x-axis. So again, 1/2 base times height, and I'll leave that up to you to do. Okay, so the last problem, last part, C, is going to ask us to instead find a value of x where the electric potential is 0. So what's happening for part C is they're now defining our final potential. They're saying that that should be 0. And we plug in our initial, which is 20, and then you set that equal to the opposite of the area, right? This would be one way to proceed. Set equal to the opposite of the area. And this would probably be your first attempt, and then what you'd say is you're going to add together a bunch of areas until you get to an area of 0, conceptually. Another way to proceed is to start from your answer from part B and say, rather than using my initial potential at the origin, then if I ignored that potential, I could say, okay, what was my potential right here that I found in part B? For me, I found that that was 50 volts. And I know that my goal here is to take it down to 0. So I do 0 minus 50, or you could just look at it as you have 50 volts in the bank and you're going to subtract off for little pieces of area. And the first thing you do is you'd calculate this little triangle in here, 1/2 base times height, which for me is going to be 1/2 times 1 times 20, so that would be 10. And I'd subtract off that 10 volts. So that would give me then 40 volts at this location right here. For me, x equals 4. And then I just need to find an area for this rectangle. I need to find an area that is equal to 40 volts. So the way that I would proceed in this case, if this is how I'm going to do it, is I'd say, okay, that is a rectangle. So that area is length times width. I want that length times width to be equal to 40. So I have 40 is equal to the length times the width. The length is going to be in the x-axis. I don't know what my final x is, so I can call that some unknown x, but I know that I'm starting on the left-hand side at x equals 4. And so this length then is just the difference between those two. So my 40 is equal to x minus 4 times the width. What is the width? It's just going to be whatever this height is, which is different for everybody, but it'd be something like E sub xs. So whatever that value is, you set that equal to the 40 volts that we want to lose and solve for your x accordingly. Okay, so that is an application of the potential difference equation. Now we're going to look at some applications for potential itself. So we did a lot of charge arrangement problems the last few weeks, especially the first homework assignment was a lot of charge arrangement problems. And right here, what we're actually going to see how much this clears up when we're doing charge arrangement. So we have two particles, and what I mean is we're going to see how much cleaner calculating with potential is. Why is calculating with potential easier than calculating with forces or fields? Is because there's no vectors. It's just a scalar value. So when I have these two particles, which are called Q1 and Q2, if I want to find their total potential, that total potential, say V sub t for total, is just V1 plus V2. And the way I calculate potential, as a reminder, is that the potential is just K Q over R. Okay, now the way this problem is set up, we have Q1 at the origin and Q2 at some distance d away. So that will go into calculating our R values, but without sort of losing any value here, we can go ahead and choose a point that we'll call X, and we'll have X as our variable, and we're going to go ahead and solve for it. Ultimately here they say we want to find two values for which the net electric potential is 0. So we're going to add our two potentials together as I have set up here, and we're going to set it equal to 0, and we're going to solve. So for each V1 and V2, we're going to have a KQ over R, where the distances is the only little bit of work that we need to do. V1 is K times Q1. Notice there's no absolute values here. So potential is a scalar, not a vector, which means it doesn't have direction. However, it can still be positive or negative, and it is still positive or negative according to the sign on the charge. On the bottom, we have the distance from the origin, since we're looking at charge 1, the distance from the origin to whatever value x we have acting here as a variable is just x. Okay, then the other value, or the other the other consideration here is the distance from Q2 to X, which is just whatever X is minus the value D down here. And so we'll go ahead and plug in the potential then for charge 2 is going to be K times Q2 over that R distance. And again, how did I define that? It's just this length right here. What is this length? It's D minus X. So D minus X, and we set it equal to 0, and then proceed to a solution from there. All right, so this is going to give one solution, and ultimately, we are going to need two solutions. This will give us a solution on the positive x-axis. For the solution on the negative x-axis, we just have to set up a little bit of a different equation. And the only thing that we need to keep in mind is that we still want to have a positive R value when we are located on the x-axis. So let me extend my x-axis out to the negative value. Sorry, we're on the negative x-axis. And we'll go ahead and define an arbitrary point x here to be a location on the negative x-axis. Now, in this case, the distance from the origin to x is actually negative x. So when I'm working with this equation, I'd have k q1 over negative x. And then I have plus kq2, that doesn't change. Now on the bottom, the distance from particle 2 to this x value is actually d minus x, because this is going to be a negative value. So we actually want to have d minus x here, just as we had before, but now minus a negative will give us plus a positive. And we set this equal to 0. And solving here will give you a negative value for x, and that will be your solution for part B. Okay, so the distances are a little funky, but I do think it's worth pointing out that this problem is quite a bit easier. Here we're solving for a distance, so we have to treat our distance variable with sort of soft hands so we don't miss something with the negative values. But the summation of the potentials here is much cleaner than with the electric fields. Now, problem number 3 is going to take this up even an additional step. Problem number 3 revisits a sort of problem, a type of problem that we had with the electric field, where we had the charged rings, and we have Q1 across a quarter of it, and then we have Q2 across 3/4 of it. And they're going to ask us to find the potential at a few different points. One point that is directly at the center of this arrangement, excuse me, and then another point which is some distance above. So they call these 2 points C and P. And just to get my diagram down here, this is Q1 and this is Q2. All right, and so we just need to find the potential at each one of these locations. They also give us that the radius of the circle is big R, and they give us that the height from C to P is called big D. Okay, so for both the center of the circle and the point P, we're going to have 2 different calculations, but in both cases, we just repeat what we did in the last problem, where we are calculating the total potential. So that's going to be the potential from ring 1, the green ring, plus the potential from ring 2, the yellow ring. And just as we did before, it's going to be kq over r squared, or kq over r, rather. And you could be forgiven for thinking that, there should be something a little more involved here. Do we have to do a lambda? Do we have to do an integral? Here's the thing. I'm going to take a step back here. Technically, yes, there is a definition, just like we had for electric field, that says dV is equal to k dq over r. Okay. Now, that definition should look similar to the electric field. And when we did the electric field, we had to do a substitution for dq. We had to integrate. And the reason why we had to do that is because, if you remember, the reason why we had to do an integral when we had the ring problem is because the direction of the electric field changed as we went around the ring. That was the point. We had the cosine theta, and that direction changed. And so we had to do infinitesimal electric fields and add them up with an integral. In this problem, though, since the potential is not a vector, there is no direction consideration. And so the potential at the center is just going to be due to the kq over r. In other words, since my distance is constant as I go around the circle, since the little r down here is big R, if we're doing the distance to the center C for part A, since that distance is the same all the way around this yellow circle, I just have constant k, constant r, and my integral is just the integral of dq, which I know the integral of dq is just equal to q, the total charge, right? So in order to calculate then the potentials, the total potential, we just have k q1 over big R plus k q2 over big R. No integral to be done. In fact, that's it. That's the problem. We're given everything we need there. For part B, you have to do a little bit more. They ask you to find the potential at point P, which is now at some height above the circle. So in this case, we know the radius of the circle, we know the height d, and so we just need to replace both of these r's with the Pythagorean square root of d squared. Whoops. Oh, that would have been fine. But this d squared plus big R squared. So it's just a different distance, but the same argument that we used over here holds, where the distance is constant, so there is nothing varying as we go around the loop, and thus the integral just reduces to the integral of dq, which is just, again, charge. So we actually do not have to do integration here, and that is, again, sort of emphasizing how clean potential is as we are using it here. Okay, now let's look at another application. Well, this is an application. I guess this is still probably a theory type of problem. This is another way that we can use potential. So this problem, we're given an electron, and it's subject to both an X and a Y potential, electric potential. And in this case, we're actually asked to find the force on the electron. So in this problem, we're using potential and we're going to work backwards. And if you look at the graphs, they both have a shape that's something like this. This one is shaped like this, and this guy is shaped something like this. And what are they for? The first one gives you potential versus the X coordinate. Second one gives you potential versus the Y coordinate. Now, in this problem, essentially, we're making use of the inverse of our definition for potential difference. Remember, we said potential difference is the negative integral of the electric field vector dotted with ds, which gave us, I said it simplifies to e sub x dx, right? We're usually just integrating, say, one component at a time. If we invert this, we can then say that the electric field is the negative derivative of potential with respect to a distance variable. So what I mean is the electric field and the x component of the electric field is just the opposite of the derivative of potential with respect to a distance variable. Now, I do need to use a certain type of notation that if you haven't taken Calc 3, you will not have seen yet, but I'm just going to use it. There are some minutiae with this notation that you have to take Calc 3 to do, but you don't actually need to do them to do anything that we're going to do in Physics 2, right? However, I still want to make sure I use the right notation. So I'm just doing derivative here. You could think of this as just like dE dx, okay? But we're using this little curly d. This is just, it has to do with the 3 dimensions of the partial derivative and all that stuff. But all we need to know is just that we're going to take the partial derivative with respect to x to find e sub x, or we will take the partial derivative with respect to y to find the y component. You know how to take a derivative, and for this problem, all it means is we just need to take the slope of each of these graphs. So the electric field component will be the slope of this graph. Oh, I should use a different color here. If I take the slope of this, that's what I'll plug in for the derivative. You rise over your run, reading the graph. We'll plug that in, and then the electric field component will actually be the negative of that, the inverse of it. And then we take the slope of this graph here to find our y component of the electric field. Of course, it'll be the negative of the slope. So you should have a positive value for the x component of the electric field and a negative value for the y component of the electric field. Now, ultimately, this problem doesn't ask us for a field. It asks us for the force on an electron. And in order to calculate the force on the electron, the last thing we need to do, you're just going to do it independently, right? It's just asking you for the x and for the y. So it's sort of two parts that we're doing at the same time. But in general, if I wanted to find, say, the x component of my force, I would just do q times e sub x. And if I wanted to find the y component of the force, it would be q times e sub y. And then the only thing that I need to make sure that I do here is note that I have an electron. So for an electron, q, the charge, is negative 1.6 times 10 to the negative 19 coulombs. All right, so this relationship between potential and electric field is sort of the core of this problem. This is stuff that we've done already in previous weeks, but we're sort of seeing how all this stuff ties in together. Great, so we can go from potential to field or from field to potential, and we have calculus definitions to do both of them now, which is very useful. The last thing that we're going to step into for chapter 24, I think this is the last chapter 24 problem. Yeah, the last chapter 24 problem that we have here is going to ask us to calculate a potential energy for an arrangement. So we have four particles here: positive, negative, negative, positive, positive, negative, negative, positive. I think they give us a break by having the same charge on each of them. And then we have side length A for the square. And we're asked to find the total potential energy now. So just as a reminder, just go back to this, potential energy is different than potential. and the potential energy is KQQ over R, and you have one potential energy for each pair of particles, okay? So in total, what I'm going to have here is how many pairs? Well, you can count them up if you want to. We have one pair, two pair, three, four, five, six. So there's 6 total pairs that we need to add up, but there is some symmetry, and you can do it however you'd like. But in general, as I'm approaching this, my uh, my potential total is just the sum of the potentials between A and B, where A and B are any two of the particles. Maybe I shouldn't use A and B. I guess I and J. It's technically a double sum, but that's just going to confuse more people than it would help. But it's technically a double sum, and you're going to have an I and J, right? So you could name each of the particles and go from there. The way that I would do this is I would look for which pairs are going to be the same. So for example, I have 1, 2, 3, 4 pairs which are separated along an edge and have one positive and one negative. So for each edge pair, we could say the potential energy of an edge pair, that'll be K times positive Q times negative Q over R. Remember, it's just R for potential energy. And the R along an edge is just A, just the edge length. So I have 4 of those edge pairs. So maybe that's the right thing to write here, is we have 4 U sub edge. And then we have 2 more pairs. What are those 2 other pairs? These ones are along a diagonal. So we'd have this pair where we have 2 negatives and this pair where we have 2 positives. So you could do each of these individually. That's one side of it. Or you could say that actually when I have negative times a negative, the negatives will cancel, and so we'll still end up with the same Q times Q on top if you'd like. If you don't see it, do each of them by themselves and add them together. But I'm just going to say here that I have one type of diagonal pair, and that for each of them we'd have K times Q. Over on the bottom, we're going to have the distance across a diagonal, which is, we know now, after doing this several times, A root 2. And so we'd have plus 2U diagonal. And you go ahead and add them together, and you'll get a final value. And of course, the units for potential energy are in joules. Great. And in all of these, by the way, as you're simplifying, you'll have a KQ squared and KQ squared. The only difference is that there is going to be a negative here. And so you need to make sure you mind your negatives, because these values are going to be negative potential energies, and these ones will be positive potential energies. Okay, with all of that in mind, we can now proceed into chapter 25. And chapter 25 is going to deal with capacitance. So what is a capacitor? Capacitor consists of 2 parallel plates. Here's one plate and here's another. I'm showing them kind of in cross section. And what happens is you connect wires to these 2 different plates and establish a potential difference across them. So you'd have some positive potential on the left side and some negative potential on the right side. And what's going to happen, this is a little difficult. So, okay, or this is an annoying point in the way that the stuff is taught, which is that the way that we proceed through physics 2 when we first learn it is with the assumption that it is positive particles that are moving. It wasn't until after a lot of these conventions were defined that the realization was made that it was actually electrons or negative charges that move. So what I'm going to do here is I'm going to talk in terms of negative charges, but you may have heard someone speak in terms of positives, but we know now it's electrons, right? Electrons are what moves. That's why these things are called electronics. And a capacitor is our first electronic device. So let's go ahead and use electrons. So electrons want to move away from this negative potential. They want to move uphill, right? Up to a positive potential. So they're going to move along this wire, which is fine because it's conducting, but then they get to this plate. And all they can do is just build up along the plate as they get there and sort of space out. And you have a bunch of electrons, but they can't jump over the gap. So the gap is filled with air, or sometimes it's filled with a material that increases the like difficulty for electrons to jump over this gap. But what is going to happen is the electrons on the other side are going to flow off, and there's going to be an induced charge. And so you'll have just a net positive charge remaining on the left plate. And when this occurs, what happens is outside of this arrangement, the electric fields will cancel each other out. This is like the two parallel sheet problem from the last chapter. And so outside of the plates, nothing's electrical is happening. But in between the two plates, you have an electric field, and it points away from positive toward negative. And so sometimes I'll ask questions about the electric field that is in between the plates. And of course, we have charge stored on the plate, and that is the thing that we are really after and investigating. Now, the amount of charge that is stored on the plates, of course, depends on the potential difference. That's one thing. But it also depends on the actual capacity of this plate system to store that charge. So this capacity is what we call capacitance. And the way that we relate all of these terms together is to say that the potential difference is equal to the charge that is stored over the capacitance C. Now, quick note, this is potential difference, delta V. At this point, sometimes people will drop the delta, which is, I think, very confusing because I've made a big deal about how potential is different than potential difference, right? It's V versus delta V. So for me, I'm going to continue to use delta V, but I just want to make a note that as you're reading through textbooks and reading through other notes, you may see some areas where people drop off the delta, but this is in fact a potential difference. You have to establish a potential difference. Now, how does the potential difference get established over these plates generally? Usually it's with a battery. So we're going to go ahead and do problem number 6. In problem number 6, we have a battery. What do they call it? Yeah, they explicitly say it's a battery. And we also encounter our first circuit. This is our very first circuit. How exciting. And this is a circuit diagram. We have a battery, we have a switch, and we have a parallel plate capacitor. And I note this is a battery because, for one, they have positive and negative. But also, the convention here is that since these two lines right here are not the same length, since they are a different length, that means that it represents a battery. When my lines are the same length, like right here, that is a capacitor. So, and here they actually label it capacitor, which is cool. And then we have a switch. Now, the switch, we're not really going to do physics or calculations with just yet. We might get to some sort of weird circuits where the switch sort of changes the way that the electricity can flow. But for the most part, we're just introducing a switch as saying, okay, nothing can happen yet. We need to close our loop. That's the whole point of the switch. And then they tell us that we close the switch. So what happens when you close the switch? You complete the loop. And now the potential difference from this battery is established over this capacitor. When that occurs, we have a potential difference that will store a charge Q on a capacitor of capacitance C. And yeah, and they give us the capacitance, they give us a potential difference. We're simply asked to find the charge. So I just solve for my charge. It's just equal to C times delta V. What is my capacitance? Mine happens to be in microfarads. Mine is 20 microfarads, and my voltage is 160 volts. So I just plug those in. One thing that I want to mention, this is why I wrote this down. The units for capacitance is farads, F-A-R-A-D-S, and micro is still 10 to the negative 6, so make sure you're converting that to 10 to the negative 6. But other than that, it's actually just a straightforward multiplication problem, and you've calculated the charge that this battery stores on this capacitor. Cool. And then we're going to have 2 more problems. These last 2 problems we're going to deal with sort of other capacitor constructions. Eventually, next week, we're going to come back to these circuits, and we're going to see how capacitors that are connected to each other interact, and how the potential difference is distributed across different arrangements of capacitors. And that's going to provide us with some puzzles to solve as we are doing some circuits problems. But for our last 2, we're actually going to just deal with different types of capacitors. So the capacitor that I defined was a parallel plate capacitor. And there is an equation for the capacitance. I'm not going to be able to pull it up. That's okay. Um, so there's an equation for the capacitance that is stored on two parallel plates. So for a parallel plate capacitor, such as the one that I've drawn here, the capacitance is 4 pi epsilon naught times, oh, not 4 pi, hold on, one sec, let me take this one more time. The capacitance is epsilon naught times the area over the plate separation, d. So again, just to label these here, the plates are going to have an area A, and there's a separation d, and it's actually just the physical dimensions under the capacitor that tells you how much capacity you can store. Obviously, as the plates get closer, the capacitance is going to go up. As the plates get larger, the capacitance will also go up. Okay. Another type of capacitor that we could have is two parallel spheres. So we had a problem like this last week in the Gauss's law chapter, where you had these two like nested spheres, and they're I think one of them was insulating, the other one was conducting. But you could have two conducting metal spheres, and in that case, you'd have like the inner one, and then you'd have your outer sphere. And in this case, our capacitance is 4 pi epsilon naught times AB over A over B minus A. What are these A's and B's? These are actually the radii of each of these spheres. So the inner sphere has a radius little a, and the outer sphere has a radius little b. And this is just an equation from the text. And in problem number 7, we're going to put it into work. The first, put it into use here. So the first part, the part A, they give us the two radii for a spherical capacitor, and they ask us to calculate the capacitance. So you just treat the smaller one as little a and the bigger one as little b, because the capacitance is always going to be positive, and you just plug them in here and here, and also on the bottom as well, of course. And you just calculate your capacitance there, and your units again are going to be in farads F. And then in part B, they ask for the plate area of a parallel plate capacitor with the same plate separation and capacitance. So obviously we're going to keep the capacitances the same. We want to set these two equations equal. The one thing that comes into play here, well, you'll have a capacity that you'll just set this equal to. So you could say that you're just setting this equation equal to the capacitance that you found in part A. But the one thing that we need to keep in mind is that they tell us that we want to design a parallel plate capacitor that has the same plate separation. So what was my plate separation in this problem here? That's the distance between the inside and outside spheres. The outside has a radius b, the inside has a radius a. So what is the distance between those two spheres? It's actually b minus a. So we want to keep that same separation, and we now want to carry this over to a parallel plate capacitor, and that means that we're going to replace d in this equation down here with b minus a. And then you go ahead and solve for your area there. All right. And then we just have one other type of capacitor that we're going to deal with in this week's homework, and then we'll be done. This will be problem number 8. And this is an isolated sphere. And there's always an isolated sphere question on the homework. And you just make use of this equation. If you just have a single object that is a sphere that is in space, then you can calculate its capacitance. And here they say we have a drop of mercury, and we're going to treat it as an isolated sphere, and then we're going to do something with another drop of mercury. So what is the equation for the capacitance of an isolated sphere? It's actually just the capacitance is 4 pi epsilon naught r, and r is just the radius of the sphere that we have isolated. Okay. So the only thing that we need here is r. We already know 4 pi and epsilon naught are all constants. I just need to plug in a radius. And what they tell us, and this is a little bit of work that we need to do in this problem, is we're actually going to take 2 drops of a radius of like 4 millimeters. We're going to combine them together. So what happens when we combine 2 identical drops together? What is the new radius? Some people, if you got this problem wrong in the first pass through, you probably said, okay, I take 2, I add together, that's going to give me twice the radius. That's not actually what doubles. What you're going to end up with is you're going to end up with twice the volume. So the volume final is equal to 2 times the volume initial. And my final volume then is 4/3 pi r final cubed. And this will be equal to twice 4/3 pi r initial cubed. Obviously my 4/3 pi cancels, but when I actually go to solve for my final radius, I'm going to have to take a cube root of both sides. And so I get that r final is equal to the cube root of 2 times whatever the initial radius is. So you take the radius that you're given in the problem, that'll give you your initial, you multiply it by a cube root of 2, and then you plug that in to find the capacitance. All right, so that will do it for this week's homework. And great, and we're gonna just continue working through. If you have any questions, as always, feel free to reach out to me on Canvas. And if not, have a great day, everybody.